814. It's titled Exponential Decay, and we're going to answer the question, what if it does not grow? And we're going to be doing something called the penny lab. So what about the situations that do not increase? In this activity, you will explore a situation that behaves exponentially, but decreases instead of increases. This is called exponential decay. Your task is you're going to follow the directions below, and you're going to model exponential decay using pennies. So trial 0, you're going to start with 100 pennies. So go ahead and fill in 100 right here. Trial number 2, you're going to dump the pennies on your team's workspace. Remove any pennies that have the tails side up. Then you're going to record the number of pennies that remain in a table where the input is the trial number and the output is the number of heads. So you're going to count how many heads you have, and that's going to become your number right here. You're going to keep the tails off to the side. Then you're going to gather up the heads, shake them up again, and dump them on your workspace again. Remove any pennies that have the tails side up, and count the number of pennies with the heads that remain. You're going to continue this process until all of your pennies are removed, or you get to 14, whichever comes first. And be sure to record your results in the table and then answer the questions below. The first 3 groups are going to bring, the first 3 teams that finish are going to bring your chart to me, and I'm going to record it and project it on the doc cam, and we'll see what's happening. 55 says, send a representative. You guys did that. Part A, where does the graph cross the y-axis? Everybody should have crossed the y-axis at 100. You all started with 100 pennies. Does it have an asymptote? The asymptote is at y equals 0. It's going to quickly start approaching 0. And then should the, it's going to be discrete. So the discrete was that it was just points, because you can't have half a penny or a quarter of a penny. So that's why it was just those dots when we looked at the points when we looked at it. It wasn't a continuous line. Question B says, is the data increasing or decreasing? Definitely decreasing. They already told us that. What does this mean about the multiplier? What do you think the multiplier is? So it's definitely less than 1, right? Because when we've been talking about the bank accounts, it's always like if it's 8%, it's 1.08, right? This one needs to be less than 1. It's going to be something close to 0.5 or something close to 1/2. Not exactly, because you all increased at or decreased at a slightly different rate, okay? But basically, it's very close to that, okay? Top of the next page, page 12 says, let's see. Part C, write an equation for an exponential function that models your data. Make sure you also write a let statement for each of your variables. Your x is going to be the number of trials you've done, and the y is going to be the number of pennies remaining. So we all started with 100, and we were decreasing at approximately a rate of 0.5, which is less than 1, which is what makes it decrease, okay? The x up here is whatever trial you are on, okay? So if you're on trial 0, anything to the 0 power is 1, and then 1 times 100 is 100. So part D says, what output does your function give when x is 0? You get 100. That means you haven't had any trials yet. Okay? Question E, could there be an output value for x equals -1? And if so, what would it mean? Could there have been, before trial 0, starting with 100, could there have been something before it? Well, no, because that's kind of weird. But, yeah, technically, you could have had 200. You could have started with 200, shaken your pennies, and then gone to 100, roughly. Okay? If you had done an earlier trial. But that would, yeah, it doesn't make sense. Okay. Question F. In the context of this situation, what should the domain of your model that you wrote in part C be? With the appropriate domain, what would a graph of your model look like? So basically the domain is all integers. Integers just means counting numbers. So you have trial 0, you have trial 1, you have trial 2, you have trial 3, trial 4, trial 5. Could you have trial 2.3? No. You're not going to just dump out part of it. You're going to dump out the whole thing, right? You have this complete trial. So it's not going to contain decimals. It's not going to contain fractions, okay? And as we said on the previous page, it's discrete. That means your points are not connected. Okay, when I graphed it in Desmos, it just showed points, right? They were not connected. All right, G. Does the graph in part F look like any graphs you've seen previously in this course? What are the first few values of the function? What is the equation? When have we done something like this? Do you remember? When we drop the ball, right? What happens to the height?
It goes smaller, smaller, smaller.
Yes, it's going to have exponential decay, okay? So that's a geometric sequence. Your numbers are going down, roughly something like 50, 25, 12 and a half, 6 and a quarter. So if you're starting at 100, it's going to have a growth factor of 0.5, which means it's declining. And then your variable is going to be what trial you are on. All right, now let's talk about this term called half-life. So there's something called carbon-14 dating, and it's used to approximate the age of ancient discoveries and to learn more about things like dinosaur fossils. Scientists have studied the rate of decay of carbon-14 and have learned that no matter how much of this element they start with, only half of it will remain after, how many years? 5,730 years, which is called its half-life. So every 5,730 years, it's going to cut in half, okay? Which is what as a decimal? 0.5, okay. So all living things on this planet contain the same proportion of this carbon-14 relative to the amount of overall carbon in their bodies. Knowing how much carbon-14 to expect, scientists can then measure how much carbon-14 is left in ancient items to figure out how much time has passed since the object was living. So, part A says, if a living object is supposed to contain 100 grams of carbon-14, how much would be expected to remain after one half-life? After two half-lives? And so on. So if you start with 100 and then you half it, you're going to go to 50. And then if you half 50, you're going to get 25. Okay? Part B, you're going to draw the graph showing the expected amount and what's remaining in your half-lives. So here's the graph. Over here at 0 half-lives, you're way up here at 100. So there's a point up here at 0, 100. And then after one half-life, you're half of that, which is 50. Half of that, which is 25. Half of that, half of that, half of that, half of that, half of that. Okay? Question down at the bottom, question C, says write an equation For the function, it looks like the one we just did for the penny trial. It's basically 100. You're starting at 100. You're going down by a half, which is 0.5. And the x is how many half-life you're at. You're at first half-life, second half-life, third half-life, and so on. Okay. Top of the next page, question 57. Okay, we're almost there. All right. I see. Okay. Question 57 says, in addition to helping you learn about exponential decay, which is half-life, can also provide insight into the meaning of exponents that are negative or zero. Using your function from the previous problem, what output does your function give when x is 0? Does this make sense? Justify why or why not. It's going to end, or if your exponent is 0, that means the trial hasn't started yet. You're starting with 100. No decay has happened. Okay? So you're starting with your 100. Unless last period somebody took some of your pennies. Say if they needed them, then they needed them, right? Here's some pennies for you. Yeah, took 25 cents. I guess you can change that into a quarter. All right, part B. According to your graph, how much carbon-14 should there be when x equals -1? Use this information to make sense of the value of 1/2 to the -1. So if you work backwards, you would get instead of taking half, you would double it, right? So what's double 100? 200. So this is what it would look like in the equation. 1/2 to the -1 power would be 2, and then 2 times 100 would be 200. So mathematically, that's what it looks like. All right. So part C says, now calculate the output of your function when x equals -2. Use this information to make sense of the value 1/2 to the -2 power. Write a conjecture. Okay, so here's what it is. If you have 1/2 to the -2 power, you're going to do something with this fraction. Who knows what it's called? There's a fancy math word for it, but there's a word that's not fancy math that would describe it really nicely. You're going to take that fraction and you're going to do something with it. Flip it, right? You're going to flip it, and the fancy math word starts with an R. Anybody know it? Reciprocal, yes. You're going to take the reciprocal, which is just 2, and then 2 squared would be 4. All right. So the same thing you can do with 2/3 to the -2. You take that fraction, you find its reciprocal, which is flipping it, and then you take it to the 2nd power. So 3 squared is 9, 2 squared is 4, and you get 9/4. Okay? This is called the reciprocal. That's the fancy math word. And then the exponent becomes positive. Changed from -2 to +2. -2 to +2. All right, so question 58 says, use your answers from part D of problem 57 to rewrite each of the following expressions in a different form. If you and your team members disagree, check your results with the calculator. Remember I showed you how to use the exponent? You can use it with negative exponents as well. You just have to hit the negative button. All right, so for part A, we have 1/5 to the -1 power. That means you're going to flip it to 5/1, and you're going to rewrite the exponent as +1. Anything to the 1st power is just itself. So that just simplifies to 5. Okay, 1 goes into 5 times. 5 to the 1st power is just 5. All right, next one, we have 5/8 to the -1 power. So we get its reciprocal, which is 8/5. The exponent becomes +1. Anything to the 1st power is just itself, so 8/5. If you can reduce it, but this one you can't. All right. Part C, we have 1/3